what I want to do is I want to give what I'll call special point setups. And so it's a variety of different setups in which you can sort of formally state and formulate similar types of questions. So let me start with sort of the easiest one. I'll let x be just the torus, thought of algebraically. So this is c star to the n. And in this setup, the special points are just the torsion points. So points all of whose coordinates are roots of unity. Let me put this here. And the special varieties, so this is just a definition I'm giving right now, there's no results in here, are what we're going to call torsion cosets. So they're cosets of algebraic subgroups by torsion points. And a sort of pretty nice way to think of all of them explicitly is you can look at a map from some c star to the k to c star to the n, where you send a point z1 through zk to something like this, where the mu i's are roots of unity, and the mi's are monomials. So the images of things like this are what we call torsion cosets. So in particular, you have sort of, you can just look at the real group structure of this, and you get more subgroups than the ones we're interested in here. We care about the algebraicity as well. Okay, so a few other observations about this space. So first of all, you can think of x as the q points, as the complex points, pardon me, of some algebraic variety over q, namely gm to the n. And so by virtue of this, we get an action of the Galois group, which I'm going to call GQ, just the Galois group of Q bar over Q. And another observation about the category of these special varieties. Yeah, on the Q bar points, say, or the special varieties. That's right. None of the C points, unless I fatten it. You're right. Another observation is that if I take two special varieties and I intersect them, I get some other algebraic variety. And if I write down its irreducible components, then all of these guys are also special. So you get this nice sort of... I'm sorry?
What are the varieties that you take now? These are images of these guys?
Yes, yes. So torsion cosets, I just mean images of things like this. Yes, that's right. I'm sorry. Other questions? All right. So now you can sort of ask two very natural questions in this context, one of which is stronger than the other. So the first one I will call Zariski saturation. I hope it's not a terrible name. I've never written it down before in a talk. I think it's pretty good. But in this context, it's also known as Lang's theorem, or rather Lang's, well, yeah, let's go with Lang's theorem. And it says the following. So I'm going to write it down in two different ways. So the first way, suppose you take V and X, some, let's say, irreducible subvariety, algebraic subvariety. Then I can ask, what are the special subvarieties inside V? And the answer is that there are only finitely many if you only look at the maximal ones. So essentially, Number theorists, for example, often care about rational points in a variety. And this is another kind of question which is related but a little bit different. So instead of asking for rational points, we say, given a subvariety, what are all the torsion points on it? So solutions to some polynomial equations and roots of unity. And then this theorem basically says that all those solutions are explained by some toral, just monomial relations inside your variety. So the reason I call it Zariski saturation is that there's another way to say it. Let's write it down as follows. So suppose you have some sequence of special subvarieties. Then if you look at their union and look at the smallest variety containing all of this, so there's a Zariski closure, in other words, the closure of the Zariski topology, and you take its irreducible components, then these are also all special. So it's saturated in the sense that if you start by looking at only special varieties and you only allow yourself the Zariski topology and sort of Boolean operations, you never jump out of that category. When X is dimension 1, then this is completely tautological. Sorry, when V is dimension 1, you mean?
Yeah.
Oh.
Is V allowed to equal X?
V is allowed to, so if V equals X, then you only have one maximal special subvariety, which is just V.
Sorry, did you give us a definition of a special subvariety?
Yes, it was right here.
Because this was an example. Did you say what you mean by torsion cossets?
So, sorry, I bungled this up a little bit. So the definition is of a torsion coset is just a coset of an algebraic subgroup by a torsion point. And you can think of them all in this way. E.g. just means here's one way to think of them. This is all of them, though.
So these are all of them.
Yes, these are all of them. You can think of all of them in this way.
Is it okay to think of them as torsion varieties?
As toric varieties? I don't think so. Toric varieties are supposed to be compact. No, then yes. Then it's okay. Yes. I'm not sure is the actual answer to the toric variety question. Other questions?
Can you repeat the V equals X equals dimension 1? You're saying it's tautological. Why is it tautological?
Sorry, okay. So I think there are two different questions. So one is if V equals X, then V is itself special. In which case the only maximal special subvariety is just V itself. So then the statement is sort of, I think somebody asked about V being dimension 1. And if V is dimension 1, then this is saying that unless V is a torsion coset, so it is a coset of a one-dimensional torus by a torsion point, you only contain finitely many torsion points. That's what it says in the case of V equals 1. If dimension V is higher, then you have to worry about sort of tori being inside there. Other questions? All right. So I'm going to try to use the slidey board, but I'm not going to succeed. Oh, this one's short. Okay.
Why do you care? I mean, cosets should look alike. Don't all the cosets look alike? I mean,
Just the introduction. I think we should probably get ahead.
Okay. Let's move on. So the other thing you can ask is for something called measure saturation. To do this, what you want to do is, so you want to assign a measure to each special variety. So this ends up being a little bit difficult in this case because C star doesn't really have a Haar measure. It ends up being infinite. So what you do instead is you define the measure associated to a special variety Si to be the Haar measure on Si intersect the points of modulus 1. Okay, so we just restrict to sort of the compact part of C star to the n. That way we can define a reasonable measure. All right, and now we're going to do one more fix, which is that if we just ask for sort of weak star limits of things like this, that's not very well behaved because torsion points are sort of dense inside S1 to the n. And so what we do is we throw in some arithmetic. So we define the Q average of this thing. And all we do is we group together different special varieties in the same Galois orbit, and we average these measures. So one sort of nice way to write it is we integrate over GQ the measures associated to the Galois conjugates of the SIs. Okay? Yeah.
Subgroups and proper subgroups and proper cosets measure 0 always? I'm confused about the definition.
It's her measure on this subgroup.
Yeah.
So the restrictions are.
It's not the Haar measure.
Okay.
It is
Yeah,
her
it's the
measure
Haar
on
measure
this
on the
subgroup.
sun. Sure. And so then the measure saturation statement in this context is that this is a really nice way to phrase it, I think. So I'm going to make a mistake. If you look at just the set of measures you get by averaging these guys, these sort of packets, as I think Ilya called them, then this set is closed in the weak star topology. So if you take any weak star limits of homogeneous measures, you get another homogeneous measure. Okay? So by virtue of sort of this phrasing of the Zariski saturation statement, it's sort of clear that this phrasing is much stronger. Because if you have sort of distribution in the Archimedean sense, you're obviously going to get it in the Zariski sense. That's a much stronger kind of statement. Okay, so that's the case of x equals c star to the n. Let me move on now to some other contexts. So the second context I want to talk about, I'm not actually going to talk about very much. So you can then talk about, instead of tori, you can talk about abelian varieties or semi-abelian varieties. Let's say over Q, so we're still allowed the Galois action, though you can sort of get by without that assumption. So then you can make all the sort of same definition with torsion points and torsion cosets. This description ends up being a little more complicated, but nonetheless, you can still phrase the Zariski saturation statement, which is known as the Manin-Mumford conjecture in that case, as well as the measure saturation statement, and they're all still true. So let me sort of shorten my talk a bit by just mentioning this and not talking about it at length. All right. So let's talk about a context which is rather different. So now we're going to let x be the modular curve y of 1, which you can think about in many different ways. So one way to think about it is as the upper half plane mod PSO2z. And so then this is isomorphic via the J function to just the complex numbers, ignoring some orbifold behavior at a couple of points, which we're not going to care about very much, okay? So I prefer to write y of 1 instead of c, because we're really going to think about it as the space that will inform our sort of notion of what special points and special varieties are. So there's a few different ways to think about it. So first of all, you can think about it as the moduli space of elliptic curves over the complex numbers. And by virtue of thinking about it in this way, we get that it's an algebraic variety over Q, in fact. So we get a GQ action. on the Q bar points, and certain varieties defined over Q bar as well. And there's other more familiar ways of thinking about it, maybe. So you can also think about it as the moduli space of positive definite binary quadratic forms. Quotiented out by scaling and change of basis. Sorry? GQ is the Galois group, that's right. GQ is always the Galois group. Sorry, I'll write G of Q when I mean the rational point of something. Okay, so this is only one-dimensional, so I want to tell you what the special points are. There's not going to be any special varieties here except for itself. And you can think about the special points in a few different ways. So if you think about it as the moduli space of elliptic curves over C, they correspond to elliptic curves with extra endomorphisms. So given an elliptic curve, you can always multiply by the integers. If you can do anything else as an endomorphism, then you say that it has a Cm or is Cm. In terms of quadratic forms, you can think about them as just images of integral quadratic forms. That gives you a Cm point as well. Sure, well, positive definite ones. So, yeah. And finally, most practically, when actually working with the subject, a lot of the time, if you think about this J map, you just look at J of quadratic irrationals. Here, quadratic irrational, look at J of it, and you get a special point. Okay? Okay, so these are all, especially if you think about it in this way, as elliptic curves, it's not hard to see that these are all defined over Q bar. So in this case, as the risk iteration statement is sort of trivial, but the measure one is very much not. So you get this theorem of Duke in this case, which says that if Si are a sequence of special points, say distinct, and we define this measure just like before, where we average over the Galois conjugates, then this converges in the weak star topology to Haar measure on Y of 1. Okay? So this theorem is, I think, still the only proof of this theorem is through automorphic forms, essentially an analog of Weil's criterion for the space. There is a dynamical approach to this theorem, which requires an assumption, but nonetheless, let me talk about it a little bit. So the dynamical approach goes as follows. So if you think of the upper half plane, one way to think about it is as PGO2 of the reals modulo the maximal compact subgroup. And now if we bring the Adels into play, which I promise won't play a big role in the talk, but they'll make a couple of brief appearances. So the Adels are defined to be, you take the reals, and you also throw in all the p-adic numbers over P, except for you put this prime here to ensure that almost every factor is actually in ZP. Then you can think of the modular curve. Well, first of all, you can think of it as PGO2R mod K mod PGO2Z. But then if you want to upgrade your thinking, you can replace this by the adelic presentation, giving you this extremely complicated way to think about a relatively simple space. So with the same kind of idea, instead of P02R, you get P02 of all the adels. Instead of P02Z, you now get P02Q, diagonally embedded. And instead of just the compact group at the real place, you throw in all these compact groups at all the p-adic places as well. And this gives you, you can show after playing with the adels that this here is an isomorphism. This is not really a deep theorem. It just involves sort of some basic number theory. OK, so a nice way, the reason really to think about it like this is that we can then think of these Galois orbits in a very similar way to the way we think about geodesic flows via this sort of formal analogy. That works as follows. So suppose you have little x as a special point. Then if you look at, let me just write the stabilizer of x. The stabilizer of x, you can write, you can show this, you can write it as the real points of some torus T sub x, which is defined over Q. Okay? And then if you look at the orbit, GQ times x, then that's just the projection of the adelic orbit of the torus times x thought about in this way up here.
Stabilizer of X flow.
I'm sorry?
Stabilizer of X flow.
Stabilizer of x inside the PGO2R.
But X lives in the quotient.
You're right. You're right. So I mean, that's true. Sorry. I noticed this mistake while running my notes. Never fixed it. You're right. So I really mean look at x in the quotient, lift it up to x tilde, look at its stabilizer, and then do this. Thank you. So basically, if you then do the same construction with, instead of positive definite forms, negative definite forms, then this torus would become split at the reals, and we get geodesic flows. And a nice way of formulating it this way is now you have this torus action, and at every single prime, you can look at the action of the torus at that prime, and you can try applying dynamics to it if the torus is split at that place. So that'll give you sort of a uniform way to think about many of these classical theorems. So then in particular, I might mess up the attribution here, for which I apologize, but if you restrict to special points x with this torus split at a fixed prime p, okay, so let's say you have some fixed prime for which this torus is always split, then you can consider the action of the torus at p for all of these different points. You can apply dynamics, and then you can dynamically prove Duke's theorem. As I think was done by Linux. Is that correct? In this context? He certainly did something very similar to it. I'm not sure if it was actually this.
I think it's taken. It's also Skubenko.
Yes, I should mention Skubenko as well. You're right. That's right. There's sort of a cacophony of these theorems, which once you put in this form, all become sort of uniformly statable. All right. That's the case of y1. Let's continue with our examples. So almost the final one I want to give before finally justifying my title on going to Hodge theory is now let's look instead of at y1 to the n. So some power. And let's see what happens in this framework. So What are the special points? Well, the special points are just points x1 through xn, where each xi is special. That's pretty simple, just an individual coordinate condition. The special varieties end up being a little bit different, and they have a different flavor to the case of the torus. So there's sort of many ways to think about them in each of these three languages. Let me give the fastest one, which might not be the most enlightening. But so let me define first for every integer n, the Hege correspondence Tn in x1 squared to just be the image of the set of points z, comma, nz under the J map. So it turns out if you look at this,
That's why this image y1,
I'm sorry, y1, I apologize. Thank you. y1 squared is the image of you look at the set of points z and z inside the upper half plane squared, you apply the J function to it, and you actually get a closed algebraic curve. Let's call that T sub n. Sorry, was there a question? I mean J. Right? From the upper half plane to y1.
So is y1 is h mod gamma or c?
y1 is h mod gamma in this case, because you have the map J to it from the upper half plane.
The j goes from y1 to...
No, J.
I'm probably confused.
Sorry, J goes from the upper half plane to y1. Yeah. All good? Okay. All right. So then a special variety to define this, well, it's any variety where you impose relations of the form either some coordinate is fixed to be some special point. That's one type of relation you can define. Or some pair of coordinates, zi, zj, lies inside this T sub n. So you impose these sort of relations between coordinates, or you just fix coordinates to be special. You do this a bunch of times, that gives you a special variety. So in particular, this includes the case of special points, where you just fix every coordinate to be something special. Okay? Okay, so in this case, we have the Zariski saturation theorem, which we can now state. So this is a theorem of Pila in 2011. And in this context, it's a case of the Andre-Oort conjecture. So if you have a variety inside y1 to the n, then V has finitely many maximal special subvarieties. Okay, so this theorem, the way it's proved now doesn't actually, well, I guess it depends how you formulate the proof. You can prove it in ways avoiding dynamics, but certainly the way it was proved initially was as an intermediate step, you would get these special varieties, which are orbits of semi-simple groups, and then you would show that if those groups kept changing, then you would apply Ratner's theorem in the form of, and the work of Moses Shah to get equidistribution and sort of bump up via induction that way. So that was sort of one of the steps that came into play. Okay. So I want to spend a little bit of time talking about the measure saturation conjecture in this case, which is that this set is weak star closed. Same thing. So this is actually a case of this is a part of what Ilya spoke about the other day. let me mention his work in this sort of framework. So he says that measure saturation is true if you assume two split places. So you assume your tori are all split instead of at one prime at two different primes. And you need an analytic input, which, let me just summarize it by saying GRH. I mean, you don't need GRH, but it's the fastest way to say something which is efficient. Okay, and let me give a very brief idea of what goes on, and I'll gesture towards what's hard about it, because the difficulty that comes up in this context is sort of the simplest, non-trivial, very hard case of the difficulty which turns up in the more general context, which I'll talk about. So you sort of get one of two different things happening. So the first case is essentially you look at these T sub n's, which show up in these special varieties as n goes to infinity, and you apply Ratner and Moses-Shah, as I said earlier. So that's sort of the easy case of what happens, which is these semi-simple groups keep changing, and you can apply homogeneous dynamics. And the other thing which can happen, and this is really the problem, is your special varieties are just special points, given by a pair of coordinates, let's say xi, yi, in the case n equals 2, where these tori are conjugate over q. Txi is conjugate over q to tyi. Okay? So in this case, I'll just say sort of in words what happens. So what happens is you have this sort of one-dimensional torus action, if you think about the Delic description. By fixing two split primes p and q, and looking at the prime p and the prime q, you get a rank 2 action, and then you can apply powerful classification theorems by people. I think the actual thing which shows up in Ilya's work is the work of Einsiedler and Lindenstrauss, which allows you to say that these things become equidistributed in some combination of homogeneous measures, and then the hard part is to rule out intermediate measures. So in sort of layman's terms, you get this sort of point, you apply the Galois action, and you get a bunch of points inside x1 squared. And what you want to show is something like this set of points doesn't concentrate near the diagonal inside, y1 squared. You want to show that it spreads out. And if you can show some sufficiently general version of that, then you can show these things actually equidistribute. But ruling out these intermediate measures is something very difficult. It's not. Well, you get there's no unipotent flow, but these Tn's, I didn't talk about it much, but they're orbits of semi-simple subgroups of PGL2 to the n. And so you get semi-simple group orbits, and that, Exactly, they're generated by unipotents. That's exactly right. Mm-hmm. Okay, questions about this? Right. So my notes here say cut question mark, but I'll include something about this despite that. One other case you can generalize from this y1 to the n case is the case of Shimura varieties, which I won't define nor say very much about, so you don't have to worry. except to say sort of just a brief summary of what's known. So in the Zariski saturation problem, which is known as Andre Oort here, it's known for AG due to the work of a bunch of people, Klingler, Ulmo, Yafev, and Pila, and myself. Sorry, I'm just naming names very poorly. Oh, AG, yeah. AG is the modular space of a billion varieties of dimension G.
For us, we will use it to say it's a quotient of SP.
It's a quotient of SP2GR. That's right. I mean, somehow none of the groups are scary if you're in this audience. And in general, it's open, and it's basically open for the reason that we can't show that these Galois orbits are even big, let alone equidistributed. And I'll say a bit more about that later, but that's sort of the stumbling block right now. And in terms of the equidistribution, or the measure saturation, it's sort of very open. And two particularly, I think, interesting questions that might be tackleable that are open in general are, one is escape of mass. Which in general, as far as I know, we don't know how to control. And the other is, once again, these intermediate measures. And I'll just end by saying that Zhang, all the way back in 2004, has results for quaternionic Shimura varieties. Basically, quotients of h to the n, which don't split factor by factor. In certain cases, he can show equidistribution actually using automorphic methods, not using dynamics at all. Okay, but that's all I wanted to say about Shimura varieties, so I don't want to delve into this world very deeply. All right, let's get to the fun stuff. So somehow, one case that I think has been overlooked when making these conjectures and looking at results is the case of Hodge structures and their moduli spaces, known as period domains. So let me say a little something about what this looks like and what we know and what further results we'd need. I'm going to do all that in 20 minutes. Okay, so first let me actually give a definition of a Hodge structure, which is a little bit long, but it's all very elementary. So a Hodge structure consists of the following things. So first of all, a lattice L, by which I just mean a free abelian group. A quadratic form Q on L, which is integral and non-degenerate. So it can have positive and negative values, they're both fine. And finally, this is sort of the tricky part. If you tensor L with C, you get a complex vector space. And what we want is a splitting of this. Sorry, I forgot to mention one more thing, which is simple, but let me write it down. A positive integer n. That's part of the data. And then we want a splitting of L tensor C as a direct sum of just complex vector subspaces, which I'm going to write as h sub I n minus I. So there's n plus 1 of them, and they're indexed by pairs of integers that sum to j, that sum to n. Okay? Such that a couple of things hold. One is if you conjugate one of these guys, which you can do because L has an integral structure, and therefore L tensor C has a real structure. There's a real vector space inside there. You just get h I n minus I. Two, if you look at the Q pairing between these guys, they should mostly be orthogonal. So this is 0 unless I plus j is n. So only opposite pairs can pair non-trivially with respect to Q. And finally, you have this alternating positivity condition. So if you take a vector inside the I n minus I piece, which is not 0, and you Q pair it with its complex conjugate, and you multiply by minus 1 to the I, you get something which is bigger than 0. So it's alternating positive definite and negative definite. Okay, and that's it. That's what a Hodge structure consists of. And so an isomorphism of Hodge structures consists of an isomorphism of the underlying abelian groups, which pull the forms back to each other. And when you tensor with C, they pull each component back to the other component as well. All right, so when you first see it, it's kind of an arbitrary definition, but no part of it is actually difficult to follow. Okay, so everything's finite dimensional, yeah, sorry. Everything's finite dimensional. So let G be the algebraic group which is automorphisms of L and Q. So in other words, if I want the points of G over any ring, this is just the automorphisms of L tensor that ring with the induced quadratic form Q. So over Q or over R or over C, that's this algebraic group G is. And so it's nothing complicated, right? It's going to be some either symplectic thing or some orthogonal thing, depending on. I'm sorry? This automorphism? No, it doesn't prove the splitting. That's right. It's ignoring the splitting. Right. So no, so that's important because in fact what G does is it acts on the set of these splittings. And that's how we're going to get a moduli space for them. That's important. So let's let M. R is an arbitrary ring, yeah. So R can be Q, the reals, or C or something. This is just an algebraic group, which, yeah. Okay. Let's let M. So yeah, so G of R acts on the set of Hodge structures on LQ just by acting on these guys. And so we'll let M be the stabilizer of some particular Hodge structure, which I'm going to call H dot. So M is going to be compact, essentially because of these definite conditions. M is going to be a product of orthogonal and unitary groups. But in general, M is going to be non-maximal. So it doesn't matter much for dynamics in general, but Shimura varieties are always G mod K, where K is a maximal compact. In this more general setting, this M is rarely going to be a maximal compact subgroup. It's just going to be some compact subgroup.
M is a real group or it's complex?
M is a real group, so M is a subset of GR. So M is not, the way I define it, M is not an algebraic group. It's just a subset of GR. And now we're going to let omega, just by definition, be the quotient GR mod M. And so what omega represents is a set of all possible splittings of L which satisfy these conditions. Okay, so if you look at omega mod GZ now, this is just the modular space of Hodge structures sort of this type. By which I mean you have to fix the isomorphism type of Q, you have to fix the dimension of the H's. So there's some combinatorial data to fix, which I don't want to sort of list out because it's a little bit long, but once you fix it, then omega mod GZ becomes the modular space of these guys, and this is called the period domain. Or let me call it a period space. I guess sometimes omega is called the period domain. It's annoying because in literature both omega and omega mod GZ are called period domains, which leads to a lot of complications. So let me call this one a period space, and I'll call omega itself a period domain. Okay, so let me list a bunch of properties that omega has. Maybe I'll leave this up on the board for a little bit longer. So properties. Okay, so first of all, and this is not obvious from the definition, but omega, and therefore omega mod GZ, has a natural complex structure. So in a natural way, it's a complex manifold. And it's not really in the way you expect. You can't, naively you would expect, well, these are complex vector spaces, why can't I just keep track of them and have that give the complex structure? But this complex conjugation makes that tricky. So instead what you do is you reframe this in terms of some filtration, and then that allows you to do something. I don't want to go into details, but there's a way to give this a complex structure in general. Omega mod gamma, so omega mod GZ, has usually no algebraic structure. So it's a nice complex manifold, but it's known you can't put an algebraic structure on it. So it's not the complex points of any algebraic variety or space or scheme or anything like that. Let me also mention that this generalizes the theory of Shimura varieties. And actually, in many ways, it's much nicer. So the definitions of Shimura varieties are kind of technically hard to follow. It's often easier to just forget that and go back to the category of Hodge structures, because you sort of keep track of much nicer data and much less group theoretic data. A lot more of it is kept just in terms of linear algebra. So that's one thing to appreciate about it. So let me give one example of this, just to give a sense of what these guys can look like. So let's look at Hodge numbers 1. So this example is 1, 1, 1, 1. And what do I mean by this? By this I mean n equals 3, and the dimension of all of these components is 1. So L is 4-dimensional, and I insist that each of these have dimension 1. So in this case, if I look at omega, what I'm going to get is sp4r modulo, instead of the full unitary group, I'm going to get the subgroup, which I'll write in the following way: U1 cross O2. So the full compact is 4-dimensional.
What's this 1, 1, 1, 1?
So n equals 3, and the dimension of each of these pieces is 1. And that's sort of the important data you need to say what omega really looks like. So then omega is this thing here. So then you can see that omega has dimension 6, real dimension 6, And so as a complex manifold, it's going to have dimension 3. So it's a pretty easy space to sort of think about. One warning I want to give is that this omega maps to A2, the usual A2, just by quotienting out by the full maximal compact instead of this thing. But that map is not a map of complex manifolds. So as an algebraic variety and even a complex analytic variety, this thing is, the study of this does not reduce at all to the study of A2. They're somehow fundamentally different. Okay, so why is the space interesting? Well, it's interesting because even though it's not an algebraic variety, omega mod gamma has to receive a lot of algebraic data. And what do I mean by this? So take X to be a smooth projective variety. Then if you look at the cohomology of X, and you restrict to a certain primitive piece, which I don't want to go into, but it's not very complicated, then this carries a natural Hodge structure. Well, I don't want to write it down, but the lattice is given by the Z cohomology, the intersection product, the pairing is given by the cup product, more or less. And then the splitting is given by the bow splitting. So, but it doesn't matter if you're familiar with it, but regardless, it's a natural way to give a Hodge structure to smooth projective varieties, their cohomology. So then if you take a family of these guys, of smooth projective varieties, like some Hilbert scheme or like the universal family of elliptic curves, whatever you want to look at, then you get a map from this, let's call it phi, from this map Y to omega mod GZ, just given by sending Y to the Hodge structure given by the fiber of Y. And you can show this map as complex analytic and everything you want. And it's also a theorem, a recent theorem due to Bakker, Brunebarb, Klingler, and myself. It's actually two theorems put together. They give you that the image of this guy is also an algebraic variety. Okay, so you have this very sort of not algebraic thing, but inside it you get this countable union.
Now, when you say you have two different meanings, suppose in your case you have a case where this map is embedded.
Where this map is an embedding.
Yeah.
Then it's trivial, this theorem.
Then you don't say anything.
Yes.
You don't describe the closure of the image.
The closure of the image. So the image is usually closed or can easily be closed.
Because Y itself is non-compact.
Sure.
So even if you have an embedding, the image could be very nasty.
Yes.
So do you?
Compactify the image.
Yeah, this is
Not at the moment.
okay.
Yeah.
Just, to understand this.
Maybe soon, but not at the moment.
Just,
Yeah. No. That's a good question. That's a good question. So I have, I think, 3 minutes left. So let me define for you the notion of special subvariety. Of omega mod GZ. And so it's actually in many ways easier again than the Shimura setting to define what a special subvariety is. So what you can do is you can take any integral vector L little l inside capital L, and insist that L is Hodge, meaning it's in the middle Hodge component. Okay? Note, by the way, that because they're complex conjugate, if L is inside any one guy, it has to be inside the middle guy, because it's integral and therefore it's real. Or do the same for tensor powers of L. And that's it. That's the definition of a special variety. Okay, so then we have a work in progress together with Ryan Keast. So that's why the little t is here. So if you assume the Hodge conjecture and the Riemann hypothesis, for very different reasons, by the way. So removing either of these would be very interesting to me. Then Zariski saturation, which I have no time to state, is true. So I'll say very briefly why we assume both of these things. So first of all, we assume the Hodge conjecture because the fact that omega mod GZ is not an algebraic variety means it's even harder to define a Galois action than it was before. Because, yeah, what are you acting on exactly? So the Hodge conjecture, whatever that is, gives you enough compatibility to define a Galois action on at least the sort of algebraic part of omega mod GZ. The part built out of images of things like this, which is some nasty, infinite, countable union of sub-varieties inside this thing. So then you can talk about Galois orbits, and you can sort of get the machine started. I'm sorry?
Which Galois?
Q bar over Q, absolutely. Maybe K bar over K for some number field, but yeah, that's right. And then the reason we assume GRH is basically the same reason you have to assume it in the Andre-Oort conjecture right now. Is that you have these Galois orbits and you want to show they're not just one point. You want to show they actually grow. And that amounts to some images of class groups being big. So yeah, I guess I'll just end by saying that you have a measure saturation conjecture here, and I think in many cases it can really be approachable. You sort of have simpler, like this I think is a simpler case than maybe many of the next simplest Shimura variety cases. And it'd be very interesting to see some results in that direction. All right, I'll stop here. Thank you very much.
Say this is a simple case, but n is 3 and you wrote there n over 2.
That's right. So
What does n over 2 mean?
no, that's right. So if n is 3, you can't insist on anything like this, because there is no n over 2. But if you take tensor powers, then you start getting even weight, and then you can insist on things like that. That's right. No, it's a good catch.
So the Andre-Oort conjecture eventually boils down to the action of a certain mysterious subgroup of a Q-tone.
Yes.
Is this theorem about some mysterious subgroup of some group, or is there some dynamic for it?
Yeah. Sure. So I don't know if Andrew, it's quite fair to say it boils down to that question, but that question is important. So yeah, it's similar. So what happens here, I didn't have time to describe. It's a little more complicated. So what you have is you have sort of G of Q, and you have some sort of Mumford-Tate torus or Shimura torus, whatever you want to call it, mapping into it. And you want to look at the image of the class group, the sort of adelic class group here inside here. So that's assuming the Hodge conjecture. We can show with Keast that this is still the setting for special points in Hodge structures. So, but there's two difficulties, right? So the first difficulty is just understanding these class groups at all. And the second difficulty is that you really have a map here and not an embedding. So all these torsion of class groups problems show up here. And here they show up with a vengeance, because for Shimura varieties, the weights are small, which means these maps are pretty close to embeddings. For Hodge structures, the maps can really be like multiplication by n you can recover by picking a correct Hodge structure. So that sort of makes it even more tricky.